Okay, so hello, my name is Freddy, and in this video I'll be explaining how I solved the first part of the project, the Cahn-Hilliard equation. We did it in two ways, where I decided to solve it in three for loops, whereas Carlos decided to use, of course, a for loop, but they used the matrix form. And the reason why we did this is that we wanted to see how the computational time was differing. So to begin with, we have these given information. We got them from the PDF file. And the first thing is that we have to randomize C. So we get this initial concentration over here. This was written over here, -1 to 1. So if we are -1, then we have one substance, and 1, we have another substance. 0, they are perfectly mixed. And hence, now here, since it is chaotic, we have to separate these substances. So I defined a function where I impose C and I get a C nu. I started with two for loops, one in the range of y direction and one in the range of x direction. And these are just simplifications. IP means I plus 1, IM means I minus 1. And I have to impose some boundary conditions because in the Cahn-Hilliard equation, I need information. Like if I have a point, I need information of the 4 points surrounding it. So what I did, like assuming that we are in this point, and of course the point after it, I don't know anything about it. So what I told the computer is that when we reach this part over here, go back to the initial grid and extract data, the same data from here, and so on for IP plus 1, I minus 1, and so on. These are also exactly the same, just to make the code, writing the final code simpler. And I'm just simplifying the code over and over. Hence, in the end, I'm solving the Cahn-Hilliard equation one time in the space domain, but I want to solve it 12,000 times, so I imposed another for loop where it solved this 12,000 times, and I was able to get these plots in the end.
So hello guys, so after we have done the first part, we saw that the code was taking so much time to calculate everything, and the main problem of that it was that we had a quite lot number of iterations because we had two for loops for the domain and one for loop for the time step. So we did a second code with less iterations, so we just used one for loop for the time step, and as we need to calculate element by element, we took it out in this code and we use metrics. So as we have to calculate F and C and we have different positions at the stencil, so we had to shift the columns to the left, the columns to the right, and lines to the up and lines to the bottom for A, B, D, and E. And here is the code, and I'm gonna press play meanwhile I explain. So here you can see these lines that we do this shifting, and then we calculate F, and then we shifting again to calculate C, and some given time steps we print the results, as you can see here on the right. So it's almost done. Let's wait just for a while. Okay, it's done. Cool. So talking now about code 25, stability regions for the ODE formulas, you can see here that we haven't gotten the same result as in the book. And basically what we had to change, instead of, because you can see the author here do all the calculations here just in one line. He used the vector just for one line. You can see these dots. These dots are to multiply the whole or divide the whole vector, and here I have to use a lot of for loops to do these calculations, and that was the way we found to translate this code. Now code 26, that there are eigenvalues of second order. You can see here that we haven't gotten the same results as in the book. The results of the books are shown in the bottom and ours and up. And one of the main difference here, not to translate this code, is that in MATLAB there is a native function to get the eigenvalues, and here in this one we had to import a library called lnag, and as you can see, you use it here, and the other parts of the code are very similar to the book, but in the Python language. Okay, so now you can see the code 27, the KdV equation by a Fourier spectral method. that you can see here, this is the output from the book, and this one is our output. And basically, it's pretty much the same thing in the last code. Is very straightforward. And here, as I said, there is a bibliothèque native in MATLAB from FFT, but for Python we have to import. From this one, I changed another bibliothèque, but it's pretty much the same result as you can see here.
Okay, so in the second part, we were asked to translate 3 codes each student. As you can see from my results and from the Trefethen book, I was able to obtain this. And this is for the code 24, and this was for the code 35. The thing is, in the Trefethen book, for code 21, he used only one for loop, whereas you can see here I used plenty of loops. I know that we were asked to keep the simplicity and the beauty of the code, but I couldn't find another ways, hence this was only for the 21st code. But in the end, all 3 codes were correct, and our results were correct. And I think the main goal of this part was to let students be confident with Python programming, and I guess this helped us a lot.
So now talking about the part of spectral methods, the part 3. I did this separate the steps we have done together. The first step was to solve the equation, the Cahn-Hilliard equation with spectral methods, was to apply FFT. This FFT2, it's because our domain is about x and y, and the C side in this C here, in this Laplacian operator. And then we apply the inverse FFT2 also to obtain the derivative in the space domain. So after we have done this second step, then we can solve the derivative of C. But for doing that, we need to apply again the same first and second step. So we apply FFT here, and then the inverse FFT to get the result in the space domain, and then we can get this result in C, and then we can keep going on and doing the update for each time step and to find the equations here. So now here just how we have updated. Then we have a C new, C old, and plus dt times the answer, that in this case is the answer is the one we are calculating in this step. So after I have explained this part, the spectral methods, we need to have some time scheme to march on time. So the first one we have tried it was the Euler equation, but it was not a very good way to solve this, because this is a linear method and we are trying to solve a non-linear equation that as we have C at cubic. So here is our result. As you can see, we start from a random mixture, and then at a final time step, we didn't get any separation, so it didn't prove to be a good scheme for that. So we also have tried to use Huge-Kuta order 4, but still we didn't get a nice result from this one, and the answer would still rely on the nonlinear term, and the method diverged and gave us worse results. So after we had tried these 2 different schemes, we decided to try the discrete cosine transfer. So we used the discrete cosine transfer and linearly stabilized splitting chain with the Cahn-Hilliard equation to get this final equation. We got this from the literature, and I'm gonna show you in the next slides the results. So we have noticed that the spectral method is much faster than the first code written for part 1, the same one that Freddy explained. But the second code written for part 1, the one that I explained, is slightly quicker than the spectral method, but the spectral method is a more accurate way to solve this kind of problem. And we tried to compare the results. So as we initialized a random matrix in the script, we took the same matrix for the first code and for the spectral method. As you can see, the output is the very same, and then you can see here and compare the results. Here the left one, the first part, but using the faster code, and this one using spectral methods. After we made sure that our code was correct, comparing the result with the first part, we tried to see the influence of the time step on it, and we saw that if you go in a range of 10 power minus 6 and 10 power minus 4, with a lower steps, the results tends to be calculated quicker. But if you go beyond that, the results diverge. And here in the bottom, we have some kind of these results for 10 power minus 3 and 10 power minus 2. And you can see here that the result is completely chaotic and the mixture is totally separated. And so as the time steps gets longer, the accuracy of the method decrease and the runtimes increase. So thank you very much for your time, and I hope you have appreciated our work.